In this video, we will cover a few terms that are important when collecting data. We will start with accuracy. When we say accurate, means the data are close to the expected correct value. So that's mainly, if you look at the first graph here, so that's, let's say that's the expected value. Then how close, the closer you are to your measurements are to the correct value, the more accurate is the measurement or the collected data. And the other term is precise, or so this can reflect in two different ways. We call it repeatability, which means we can repeat the same experiment, or we can collect the same data multiple times, and also that's related to resolution. So when we say repeatability, which means if you look at this one or this one, so if we do the same experiment multiple times, we get results that are measurements that are close to each other. So that means it's precise, or it can be repeated and we still get something reasonable and acceptable. The same thing here. But if you look at this here, you can see every time if you repeat the experiment, you get different measurement. So that's not precise. Resolution, it can depends on the instrument that you use. So that's mainly the smallest measurable increment for your device. So that does it measure in let's say in tenth or hundredth or thousandths. So it depends on what's the smallest the instrument can measure. Is it 0.1 or 0.01 or 0.001 or 0.0001? So that's mainly what we see there. So the smaller the number or the increment, the higher the resolution for the instrument. So that mainly both repeatability and resolution are a reflection of how precise you can get. So let's look at the graph here, and again, if you see, this is the results are close to the correct value, so that's accurate, and also the results are repeatable, and we can get multiple of them close numbers, so this is also precise. If you look at this one, it's repeatable, but because we kept getting almost the same result, but there is a deviation from the correct value. So if this is the correct value, so that maybe we'll talk about error. So there is some kind of error that either your device is not calibrated, so that's mainly you are not getting accurate results, but it's precise because mainly you can see you are getting measurements that are close to each other when they are repeated. This one relatively accurate because again this is the correct value, so you are mainly relatively around the correct value, but it's not precise because sometimes you get less, sometimes you get more, so that's not repeatable here. This one, it's not repeated, it's far from the correct value, and also it's not precise because you can see the values are all over. So I hope that can help you understand the meaning of accuracy and precise, and the difference, and when do we use each of them. So let's look at different types of errors. So mainly we'll learn about two types of errors here. We call it systematic error, which is, as the previous example we said, let's say if you keep getting something, let's say if you have a scale and the scale is not calibrated, and it's always even if nobody, let's say no objects in the scale, it measures I don't know, 0.2 grams or something like that, then you are always going to get the results shifted or deviated from the correct value. So that's mainly, in this case, it's, let's say, less than, if this is the correct value, then it's repeatable. So this is a precise, but we are not getting accurate result because that mainly there is a systematic error. And this is something is usually systematic error can be avoided, and merely by fixing the device or whatever, just eliminating the source of that systematic error. If you look at this type, this is called random error, and as you can see, it's all over. So that's, I mean, just like observation, when we observe something, if you just do the same thing twice, the first time you may read the graduate cylinder or the ruler, your eyes then may just see them different, or as a human, if multiple people are doing the same thing, everybody could give different results. So that's called random error, and usually this is not as easy to get rid of as like the systematic error. Okay, the next term is propagation of error, and that's merely define this as if you start with a small error in the measurement, but it has a big impact on an equation. So that's usually the equation you have may be highly sensitive to certain measurements on that, and we'll look into one example. So that's merely you start with a small error, but it will be magnified and has a significant impact on the final results that you get. This if you look at this example, this is if we have a beam and moment of inertia, which is kind of property for beams. This is how it's defined for rectangular cross section, 1/12 times the width, which is what you see here, the width of the beam. T is the thickness times the thickness cube. So that's the definition of that moment of inertia for the beam here. And let's say if we are trying to measure to measure, so it does not depend on the length here, so you don't see the length here. If we are trying to measure the moment of inertia for this beam, which one do you think will be this the moment of inertia, which is I, is more sensitive to? Is it the width or the thickness? Looking at that equation, you can see if we have a 10% error of in the width, it may cause maybe 10% error in the moment of inertia. But for the thickness, because it's cubed, so you can see this will be magnified. So whatever small error will be tripled. So that's why it's more sensitive to thickness than width, and this is what we mean by the propagation of error. So if you are using the same instrument to measure the width as the thickness, and if you make the same amount of error or percentage of error in both, the impact of the error in the thickness will be much higher than the impact of making error in measuring the width. And let's look at the calculations just doing that. So if we have a beam, again, this is the cross section. We don't need to worry about the length, so the width and the thickness. So mainly use the caliper or scale to measure the width and the thickness. And again, this is the equation, 1/12 width times the thickness cube. And this is the width in inches and the thickness in inches too. And if you do that, the base case, I mean, if that will give you that the results for the moment of inertia. So let's now assume that we make around 10%, like 9.5% error in measuring the width. So you can see that, sorry, less than that. So instead of having the width 3.4, we measure it as 3.096. And assuming also we did the same error in our instrument can measure less. So the original, instead of measuring the thickness as 2.129, it's measured the thickness as 9.5 less than the original or the true thickness. So that's 1.927. And if we apply that into the equations, you can see you get this is the correct value, but by doing the error, you can see that that difference was around 9.5% error, which is kind of the same error that we started with. But when we applied the error in thickness, maybe by measuring the thickness as less than the true thickness, the difference was 25%. So that's mainly because, as I mentioned, there is a cube there, so that will magnify the error. So that keep that in mind, that sometimes some of the measurements are more sensitive, or the equations like moment of inertia, error in measuring the thickness is more serious than making error in measuring the width.